All right, so this time we're going to cover MIPS architecture basics and our first 6 instructions. We kind of saw these in the previous lesson, but it was kind of just a quick copy paste. Let's make this work and we'll move on. So this time we're going to dig in and we're going to really get to understand these instructions. So the first thing to realize, inside of a processor, you have memory. You have lots of different kinds of memory. But the fastest memory is the registers themselves. This is like right in the absolute center of the CPU. And in the MIPS world especially, everything has to come from either a memory location, like data out of RAM, or is actually included as part of the instruction. And we'll see a lot of those in these first few. So sometimes data is part of the instruction. And so that data has to come and get placed into a register. Then you can perform an operation on it, whether it's bit manipulations, simple addition, subtraction, multiplication, division, all your basics. But it has to all be put into the register before you can take any action on that data. And then you have to put it back out to memory where you want it. So it's referred to as a register architecture. All right. So that's the registers. They're in the middle. They're the fastest. Next, there is a cache, and there's an instruction cache and a data cache in the MIPS, N64's MIPS CPU. And that is a little bit confusing. We're going to see a little bit more about that when we start talking about the hardware in the next section. But for the most part, we can actually kind of avoid it. Or work with it, really, is what it ends up being. After the cache is the normal RAM, and the next slowest is actually the cart memory. But it's still much faster than an optical drive, for example. So there's still a lot of potential there. It's just a little bit slower than regular RAM. All right, so those are the types of memory. And so that's kind of the quick version. Sorry, reading through my notes for a moment. I do see a few people have joined. I am monitoring the chat as we go through, so speak up if you have questions. And so we covered registers. They're the fastest. MIPS is a little bit unique in that there are 32 general purpose registers in the processor, and each can hold a 64-bit value, which is 8 bytes of data in a single register, which is really cool. And it makes things a lot easier in trying to manage all of this stuff. Of the 32 general purpose registers, 2 have special behavior. The first and the last. That's 0 and 31, because everything's 0 based. The other 30 are available for any use, but there are some conventions that are used to maintain compatibility with other compiled languages. For example, when C uses inline assembly or has assembly source files in the same project. And so we'll make a point to follow these conventions in this series, and we'll refer to the registers by their more descriptive names. And then I've got... So once again, reminder, the n64dev.org, a lot of great resources here. I have a few other favorites, but real quick, we'll look here. This isn't my favorite representation for all of these, for the register names, but it's all valid and correct. So there we go. The only thing that I really don't care for in the official list, and I'll probably include this this listing in my in the GitHub when I'm done, I'll keep it organized. This list, the part that I don't care for is things like T0 to T7 and then T8 to T9. They are technically in a different sequence, but really, as long as you always refer to it as the T series, it'll always be T. And then the same thing actually applies to the S0 through S7, and this one will be using it as S8 later on. So again, we don't care what these numbers are as long as we always refer to it by these names, and that's what we'll be doing in this series. So this is my descriptions here. The register 0, and I've got a name for it of 0, so we can make that a little more clear. But it's always 0. You can't write to it. It will fail silently. Mag Striker mentioned that you can write programs that fit in the cache. I didn't mention that. That's a little bit more advanced, and we'll get there. All right, so 0 is always 0, but we'll see some cool tricks as to how you can use 0 to your advantage. It works really great in comparison scenarios, in your if conditions, essentially. Also, if you need things like all Fs, you can actually use things like a -1. We'll see those later. The AT register, we'll cover pseudo instructions really soon, but it's really reserved for that scenario. And then function arguments by convention are passed as A0 through A3. And then the return value is normally only the V0, but there's going to be a time when you want to use more than that, so V1 is also reserved. T1, it's real easy, so they are temporary. It's easy to think of them as a local function variable. So when you're defining your variables and you're working inside of this function, if you try to only use the T variables, or the T registers, and that'll be less for you to save and restore if you need more, or we'll see them in use. It'll get confusing here otherwise. And the saved registers, those are the ones that any function should be able to depend on. And so you have to save those, any of them that you use, and restore them when you put them back. And you can kind of treat them as global variables. So the K0 and K1, those are reserved. The K stands for kernel, and those are used by the exception handlers. And we will be covering an exception handler later. So we'll be using those then, but only in that case. The stack pointer. This is a really cool trick and cool register, and we will be using it for what it's intended, and that will be saving the registers, anything that we need to besides the T registers. And then R31, also called the RA, is the return register. Some of the branch instructions and some of the jump instructions will use that. Technically, it's possible to jump in and use it for just a moment, but as soon as your code jumps or branches anywhere, there's a high risk of it being overwritten. So best practice is not to do that. So real quick, that's the registers. And so then we'll go down and let's start talking about assembly language code and how we're writing the code. So the first thing I'll point out, Python is really, white space is important, and that is not true for assembly language. White space, you need to have a white space here, But it doesn't matter if this is none or a tab or 5 spaces. Just the formatting doesn't really matter. It just uses the spaces to separate different values. Really similar to all of the C-based languages, C, C++, and C#, for example. So with assembly language, you always have the instruction at the beginning of the line, and then between 1 and 4 parameters. There are a couple of instructions that have no parameters, but those are very special use cases that we'll see in the when we use those. And very similar to the C-based languages, and I believe this applies to MIPS specifically, is that the instructions usually read right to left. So as an example, we're looking at this LUI instruction. Its pif base is a constant, and so the value of pif base is going to be placed into the T0 register. And so in this case, the add immediate is actually going to take the value 8 and place it into the T1 register. The store word is one of the few instructions that actually does read left to right. And so in this case, T0 is a memory address, pif control is an offset. We'll cover this in a little bit more detail. So between these two, we now have this address, and we're going to take the value that's in T1, which is 8, and we're going to write it to this memory address. And so that is the store word. So let's see. That's kind of the overview of how these things are formatted. Next, let's get a little bit more specific. So I tried to include, once again, a C-based language example over on the right side. So LUI is to load upper immediate. So the immediate instructions mean that it has data as part of the instruction. In this case, it's this value of pif base, and we can reference pif base and find that it is this BFC0. And so load upper immediate. For the most part, the registers, they're commonly treated as 32-bit, even though 64 bits are available. And we'll see in most cases, 32 bits is great, and that's all we need. There are a few instances where we'll use more, but this is a great place to start. So what happens? So it loads the immediate value, that, into T0, but the upper portion of that instruction is this part. So it's taking this 16-bit value and pushing it up 16 bits. And so it's the upper 16 bits of the 32-bit portion of the register. I hope that makes sense, and we're going to see this here in a minute, so don't worry if it's not clicking for you. And then here, this is the add immediate instruction. And here we can actually, we'll use our 0. Because technically, this instruction uses 2 registers. And what it's doing is it's going to take the constant value of 8, and whatever value is in this register, which as we know is always 0, and it's going to place it into the T1 register. And so that's the first example of how you use the 0 register. Okay. And this is really just a very simple assignment. Here we can say this is actually 0 plus 8. And that's being placed into the T1 register. So pretty straightforward. The thing about assembly language is it's really step by step with very small steps. In Other assembly languages get more detailed and more involved, and yeah, MIPS is kind of that higher level. It's a reduced instruction set. It really has a lot of very simple instructions, and we're going to find with about 10 to 15 instructions, probably 15 instructions, we'll be able to put something on the screen that we can recognize. Not like a photograph per se, but we can start to draw boxes on the screen with 15 assembly language instructions. So that's a pretty cool feature. The SW instruction is store word. In the MIPS instruction set, a word is 32 bits. The different types that you can do here, there is an SB for store byte, SH is store half word, SW is a store word, and then SD is a store double, which allows you to write out all 8 bytes out of a 64-bit register into a memory location. And all right, so those are those 3 instructions. Let's see, yes, and so loop, by using the colon, so it doesn't matter the text that we use. This is just a convenience thing. The colon is what tells the assembler that it is a label. It is a target for something. And so in this case, we have J all by itself, which is a jump instruction. So all it does is go to loop and come back. And so it's the same thing as this while true statement from, a C syntax. All right. Real quick, I'm trying to decide if this is going to confuse or clarify for enough folks here. You know what? We're just going to stick with this. So I just saved that, and I'm going to open up my command line and oops, went off the screen, and just going to rebuild that and then run that. Real quick, if folks haven't spent much time with DOS, I actually used quite a few shortcuts here. I'm going to go over them really quick because I do them a lot. And so the first thing is, once you do like a slash or anything, so slash refers to all the way down at C root. And so once you do that, I can type G and then the tab key, and tab again will get me to the GitHub folder. And then a backslash again, and F for Fraser. And so again, this is just the backslash and tab keys. Just allows you to navigate very quickly. And then other than that, I was just using dir, which is for a directory listing. Just kind of tells you where you're at. So pretty basic. And then we did a make, and we have our, actually I want to use the debug. And so I'm just using tab. The first file is the ASM. The next is my ROM file. So I'm going to debug that. All right, so we kind of covered before that MAME starts at the very first instruction in the PIF or the BIOS of the N64. And I am going to do BP set 8, 1, 2, 3 zeros, 1, 1, 2, 3 zeros. And this is the first instruction of our code that will get executed. And so now I'm going to press F5, which is just right here, and it just says run. And boom, there's our instructions. So that all of that BIOS code was using the registers, which we can view here on the left side. And so that's why there's already some values in there. But for the most part, we don't really care about those. So first, we're going to look at this LUI. This is the load upper immediate instruction. And it says that it's going to put the value of BFC0 into T0. But as I said, it's going to push it up 16 bits or 4 hex characters. So we'll find the T0 register, which is right here. A4, so the upper 32 bits are set to F, and then the A400200. So we will do F10, which is a single step, and now we can see our new value as the BFC0 in the upper 16 bits of the 32-bit portion of the register. So a little confusing, but that's why it helps to actually see what's going on. All right, so next up, we're going to put the value of 8 into the T1 register. And again, F10 to step. And now we can see that T1 is all zeros with an 8. Okay, so real quick, I'm going to cover the Fs. Why does the T0 have all these Fs at the beginning, and why does T1 have all zeros? It's a concept called sign extension. If we come here, this is, we're going to go to hex. We'll go BFC0, 1, 2, 3, 4. Yeah. In the previous video, I said that I really like the Windows 7 version of the calculator, and this is going to be one of those cases. So BFC0, 1, 2, 3, 4. So here we can see that this bit, the very highest bit here, which is the sign bit, did I go the clearest way I could here? What's happening in the register is there is no sign bit on T1, or it's a 0, so that's basically off. And so whatever the sign value is gets extended for the upper 32 bits in the register. So that's why we see several other values that start off with those Fs. So whatever's in that top bit of the first 32 gets extended out. And so BFC, as we see here, that top bit is a 1, and so that's what gets pushed out. It's a little confusing. Most of the time, the cool part is that it actually doesn't matter. But I just kind of wanted to explain that. When we get to cases where it does matter, I'll probably spend a little bit more time with it. In the meantime, just know that that's what it's supposed to do, and it's this upper bit that's telling it to do that. Okay. And so then we have... So now we have our two registers set up, T0 and T1, and I'm going to open a new memory window, and I'm going to point it to BFC007FC. And so we can see here that we do have a C0. Again, this is a PIF value that's just remaining in this location. And so next we will put the value of 8 right into that little memory space. Just that easy. And here's the jump instruction. And here we can see that it's pointed to the address of our loop label, which should be pointed at itself. And what we see here is that the address of the jump instruction matches the address of the destination. So we have the concept of a delay slot, and that is the instruction afterwards. So when we look here, we have a NOP, which is a no operation instruction. This is one of our few that don't have any parameters, and once again, it's no operation. It doesn't seem like it's going to be very useful. When we're using a delay slot, it becomes very useful. And delay slots, once we start to really use them and try to optimize our code a little bit, we'll start using the delay slots a lot. So in the meantime, I'm going to do F10 here, and we're just stepping back and forth. So it's jumping. The jump is jumping to itself, but part of the jump is executing the delay slot, which is right below it. So those concepts will all make a little bit more sense as we go along as well. And so there's one more instruction that I really wanted to cover at this same time. And it seems a little strange, but it kind of comes back to that sign bit. And just so people know, the sign bit that we see here, this is how all operating systems, well, all the ones that I know of, actually store a number that can be positive or negative. And if you are familiar, or even if you're not, let's see, we can say int range. I'm going to use C once again just as our simplest example here. So here we're going to basically focus on the 4-byte version. And so a 4-byte integer, which is signed, has a range from a positive 2 billion to a negative 4 billion. But then when you have an unsigned integer, it is 0 to 4 billion, plus some change and such. And the reason it does that is because of the signed bit. When the value is signed, the uppermost bit is, when it's a 1, it's negative. So that's kind of an interesting note. When it's positive, it's a 0. So here, I'm going to switch this over to a decimal value so that we can see the numbers. And I can toggle this. Oh, but it's not thinking in positive and negative. There we go. And here we have the sign extension. When I selected that, you can see all of those upper bits got flipped, and so now they are that F value. And so again, sign extension most of the time happens in the background because we're like staring at the debugger, going through our code. We're just going to see a whole lot more of that. And that is what I had planned on covering with the first 6 instructions, and just kind of understanding the registers and how those worked. So I'm gonna continue on, but I'm gonna switch topics, and in doing that, I am going to stop this recording so that it's separate when I archive it out onto YouTube.